We're moving on with this excellent chapter. We've had a good run here of things that we can do with the first derivative and second derivative, applications of derivatives. So we're here, gather here today to add one more to our list. We're going to add the mean value theorem, that one right there. So I've already reviewed these many times. I'm just going to get to it. It's kind of a biggie, so let's do it. The mean value theorem starts off with something a little bit more mild called Rolle's theorem. Now, Rolle's theorem says, roughly speaking, that if you've got a function here and you've got some value, I don't know, at 3, suppose it's equal to 5, and suppose you go further down to the right, blah, 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 whatever, just to say 7, and suppose at 7 it's still the same height, it's still at 5, no matter what happens here in the middle, if the function is continuous and differentiable and well-behaved and all that, if it goes up at one point or another, it must come down. Roughly speaking, that's what Rolle's theorem says. Whatever goes up must come down. If it starts at 5 and ends at 5, it must have come back. But more specifically, what it says is that it must have some point here within that range. It's got to have some point here within that range such that at that point, since it went up and then it came down, at that point, the tangent slope, if you look at it really closely, it must have been not rising. It must have been just flat. The fancy way of saying that is that there must be some point here in the middle, some point C, such that f prime of C is equal to 0. It's pretty obvious from the picture. The proof is still interesting. Excuse me, I think I posted it as one of the homework exercises for you to think about. The statement formally could be said something like this. If f of A is equal to f of B, and B is larger than A, or whatever, they're different, then there must exist, this is a symbol for there must exist a C inside this interval, A, B, that's how you say a C, that's a member inside that interval, such that f prime of C is equal to 0. A fancy way of saying that, hey, whatever goes up must come down. And when it started to come down and when it stopped going up, it was flat. That's really what the Rolle's theorem is saying. And we can actually try a little example just for fun. Here's a famous curve. This is called the sine curve. I'm sure you've heard of it before. Y is equal to sine x, right? Starts off at 0, 0, peaks up at pi over 2. I've got my stuff here in radians, and it goes down through 0 at pi, etc., etc. It's periodic. It goes forever. Now here's a curious example here. If I look at my function here, sine of 0 is equal to 0, and sine of pi is equal to 0. It started at 0, it ended at 0, it went up, it came down. What does Rolle's theorem say? Hey, there must be in the middle where some points within it, not necessarily exactly in the middle, but within this range such that at that point, I'll make it a different color, some point here C such that at that point the tangent slope was exactly 0. So it's almost a common sense idea, but it's got Rolle's name attached to it. Very nice, simple. And we can actually do the math here just for fun. Y is equal to sine x, and then the derivative would be cosine x, and the theorem says that there must be a point here somewhere where cosine of C is equal to 0. Which point would that be? Well, of course, you can solve this equation from your trig class. You'd see that C equals 90 degrees is one of the solutions. So there it is at 90 degrees. The cosine is 0, meaning that at 90 degrees the derivative of sine is 0. Told you. Pretty straightforward. We can do it again, maybe with something that's not a trig function. Let's take a standard parabola here. And let's look at, by the way, Rolle's theorem could also be looked at upside down. Whatever goes down must come up. If it started at height, it was 4. See, this line is y equals 4, and it ended up at y equals 4. Whatever it did in the middle, if it was continuous and differentiable, it must have peaked somewhere at the bottom, and at least once. It could have peaked several times. I don't know that. But at least once it peaked, and at that point it stopped going down and it started going up, and so at that point it was flat. At that point, f prime of C must have been equal to 0. That's what Rolle's theorem says. And you can actually do some numbers here just to get a feel for what the theorem says. This is 2x minus 3. You set it equal to 0. Say, hey, I'm looking for the derivative. I'm looking for places where the derivative flats out. Tangent slope is flat. Set that equal to 0 and you get that 2x is equal to 3. Or said differently, a 3 is over x equals 3 over 2. And there you go. Whoa, 3 over 2, that's 1.5. Whoa, look at that. You can't look at that. Now you can look at that. Look at that. 1, 2, 1.5. At 1.5, consistent with the picture, the mathematics here, the algebra tells you that at 3 over 2, the graph was flat. If you were to zoom in there, they're almost indistinguishable. That's what Rolle's theorem says. Pretty basic, right? But that's not really why Rolle's theorem is important. The reason Rolle's theorem is important is because it proves something else. Rolle's theorem, if you take it up a couple notches above, it turns into something a little bit more general called the mean value theorem. And I would say perhaps that's really why Rolle's theorem is most important, because it helps prove the mean value theorem. It's a little baby version, preliminary version of the mean value theorem. This is the real deal here. The mean value theorem. And of course you'd want to ask, well, why is the mean value theorem important? Well, you'd have to wait for that, right? I was saying that the importance of Rolle's theorem is, the most important thing is that it delivers the mean value theorem. So let me tell you what the mean value theorem says. Roughly speaking, it says that if you've got a point here, any old point, say 3, and you got some other point here, any old point 10, and say at this point some function has a value of I don't know, 2, and then at 10 suppose it's got a value of 16, then you know, the secant slope, this would be the secant slope, would be rise over run. You would calculate the run. Oh, the run is 7. You would calculate the rise, 16 minus 2. That would be 14, and so the slope would be 14 over 7, which is equal to 2. That's called the secant slope. Now the function itself, it could have been doing anything here. As long as it's continuous and differentiable, it's smooth, it could have been going like this, or like this, or like this, or like this, or whatever. What the mean value theorem says is that, hey, if it went on average of, if it rose an average of 2 whatever units, 2 y units per x unit, at some point within this interval from 3 to 10, it must have attained exactly the same secant slope, but as a tangent slope. Meaning that there must be a line somewhere within here, at least once, where the tangent slope right there is exactly the same as a secant slope. And in fact, in this case, according to the drawing, it occurs at 3 spots. Okay? What that means concretely is, here, I'll give you an example. Suppose this is a position function, right? This is a position function. And so suppose you've moved from 2 miles to 16 miles. That's your change of position. You moved a total of 14 miles. And suppose this was done in 7 hours. The secant slope could be interpreted as 2 miles per hour, being the average between the 3rd hour and the 10th hour. You average the total of 2 miles per hour. That's what the secant slope is. The mean value theorem adds something to that. It says, hey, at some point or another, at least once within this period from 3 to 10, you had to be going at exactly the same speed as the average speed. The average speed is 2 miles per hour. You couldn't have always been traveling at lower than 2, because if you had been traveling at lower than 2, you couldn't have averaged 2 miles per hour. You couldn't have always been traveling above 2, because then you would have averaged more than 2 miles per hour. So some of it may be above, some of it below, or maybe all of it at exactly 2 miles per hour. But at one point or another, you had to hit that mark. You had to be going at exactly 2 miles per hour. That's the interpretation of the mean value theorem. And we can actually try it on some numbers just to get a feel for it. Let's practice the mean value theorem on this silly little example. We pick a couple points, first of all, to practice our mean value theorem on. This one, 3, when x is 3, I could plug it in there, I get y is equal to 4. So f of 3 is equal to 4. Here, f of 1 is, I could plug it in there, I get 2. F of 1 is equal to 2. And then I draw my tangent slope. My secant slope. That's it. That's the average increase of the function. It averaged, let me see, I can calculate rise over run here. or I could just do it the normal way. F of 3 minus f of 1 all over 3 minus 1. So that means my secant slope was equal to 4 minus 2 all over 2. So that means it's equal to 1. On average, you run 1, rise 1, run 1, rise 1. That's what the function is doing on average from 3 to 5. Now, what does the... I'm going to erase this so I can make it look cleaner. What does the mean value theorem add to this? The mean value theorem adds to this, hey, there's got to be a point somewhere within the 1 and 3 range where the instantaneous rate at which the function was increasing is exactly the same as the average rate at which it was increasing. On average, it increased 1. There's got to be a point somewhere within this range that the tangent slope is, where the tangent slope is also equal to 1. And you can even kind of eyeball it here. If the graph is accurate, it's probably somewhere around there where this slope is exactly the same as that slope. But you don't have to eyeball it. You can actually do the math, and that's what I think would be useful to practice here. F of x is equal to 2x minus 3. That's my formula that describes all my tangent slopes at any given x. I'm looking for one where the tangent slope is equal to 1. So I move the x over, so I get 2x is equal to 4, making x equal to 2. Exactly, I suspected based on the graph, at exactly x equals 2, the tangent slope is equal to 1. It's equal to the secant slope as promised by the mean value theorem, which said, hey, always, if the function is nice and continuous and differentiable, I can always find a spot within the range where the tangent slope is the same as the secant slope. It's almost the same version of the Rolle's theorem, except Rolle's theorem would tell you, hey, if you're flat here, then the secant slope is 0, so there's got to be a point where the tangent slope is 0. You can almost think about the Rolle's theorem as a baby version of the mean value theorem. Or if you want, you can think about the mean value theorem as the mama version of the Rolle's theorem. Just kidding. Anyways, want to try one more example? Let's try one more example. By the way, the mean value theorem doesn't say there's exactly 1 point. It says there's at least 1. So there could be more than 1. Take this example just for fun. F of x equals x plus 2 sine x. So it's wavy all over the place. You could take a couple points here. Let's say, let's go with red this time. So we go with that point, and we find the secant slope. So what is the secant slope there? Well, let's see. This is the secant slope would be f of 7.5 minus f of 0 all over 7.5 minus 0. And you could crank that in the calculator. Crank that out in the calculator and make sure you're in radians, and let's see what we get. So I changed my calculator to radians just because the graph is in radians. We'll keep it all in radians. I'm trying to calculate the secant slope, so you just plug in 7.5 whatever. You get that the secant slope is 1.25. So 1.25. So what does the mean value theorem tell you? It tells you that there's at least 1 point within this range from 0 to 7.5 where the tangent slope is also 1.25 approximately. Now you don't have to think that hard to see exactly what's happening here. You could see by just looking at the graph that somewhere around here, somewhere around that point right there, maybe this is 1.5, somewhere around 1.5 point, and also right around here you have a tangent slopes that are the same as the secant slope. So if I solve this equation, the mean value theorem says there's at least 1 point that will match the bill, but in this case, by looking at the graph, I think we have 2 points. But you don't have to guess, you just solve the equations. F prime of x, and that's what I think is instructive here, is equal to 1 plus 2 cosine x. Now I take that 1 plus 2 cosine x and I set it equal to 1.25, because that's what I'm looking for, places where my tangent slope, this is the formula for my tangent slope, is equal to 1.25. That would give me that cosine x times 2 is equal to 0.25, or that cosine x is equal to 0.125, or that x is equal to, now I get a whole bunch of solutions. Look at the cosine graph here. I'm looking for places where it's equal to that 0.125, so it's going to happen before 90 degrees and a little bit after 270. Okay, so I solve cosine. Let me think. Cosine of 1.25. So I got to do a little cosine inverse. So I'll do a cosine inverse of 0.125, and that gives me my first one, 1.44. Let me see if I can show you in there. 1.445 is exactly as expected on the graph here. 1.445. I've got myself a point where the tangent slope matches the secant slope. That's exactly what the mean value theorem promised. But incidentally, we have another solution to that, because if you go 360, which is 2 times pi minus that answer right there, that's because I go all the way to the 2 pi and then come back, whatever this distance was, I can come back from here and get my other distance. That would be 4.8. Can you see it? I'm just going to round off to 4.84. Why not? 4.84. Exactly 4.84. Exactly as expected. We've got the same thing happening again. The tangent slope matches the secant slope as promised by the mean value theorem. That, my friends, that's what the mean value theorem says. Again, you could do a little example here. If at one, after, you could graph something like from real life, like say you have a position. Say you're measuring the position, you're walking away from your house. Say you get mad at your wife or something. Not that I ever get mad at my wife, but suppose somebody has a unfortunate situation where they get mad at their wife and they have to walk away, and they just start walking, and after 1 mile, after 1 hour, they're 3 miles away from their home. After 7 hours, they keep walking in like Forrest Gump, and now they're 21 miles away from the home. Now, you may not know what happened here in the middle, but the mean value theorem tells you something about what happened in the middle. Maybe you walked a little bit, maybe you rested, maybe you stayed still, maybe you walked really, really fast and you just ran and then you ran out of energy. I don't know, something crazy like this happened. But assuming you were continuous, you didn't appear and reappear somewhere else. It probably looks something like that. But the mean value, even if you don't know all the details, the mean value theorem tells you something. It says, hey, I can tell you something. On average, over the 6 hours, you traveled a total of 18 miles over 6 hours. So the average rate was 3 miles per hour. You were walking at about 3 miles per hour on average. And the mean value theorem says, even though I don't know what happened in the middle, I know something about what happened in the middle. At one point or another, between the 1 and the 7 miles, you were walking at exactly, if you had a speedometer, you were walking at exactly the same rate, 3 miles per hour. The tangent slope here, f prime of c is equal to 3 for some point c here. At least once you had to cross that. Because think about it, it's almost common sense. If you had always been walking below that mark, the 3 miles per hour, you couldn't have averaged 3 miles an hour. If you're always walking above, you would have averaged more. So at one point or another, you had to be walking at exactly 3 miles an hour. That, my friends, that's the mean value theorem. And if you stop there, that would probably be pretty good for an insect. But actually, the mean value theorem is so much bigger than that. It's deeper than deep. And I think I'm going to pause the tape here and try to tell you exactly why. This is the most important question right here. The importance of the mean value theorem. Why is it important? Why is it important that between the interval from b to a, this is the secant slope, this is the tangent slope, there exists a point c that matches exactly the secant slope? It almost seems like common sense. What else, what could you get out of that? Oh, my friends, you have no idea. Or maybe you do, but let me just catch my breath and let me try to put the story correctly as it should be. I don't have any mixed feelings about the mean value theorem. Okay, so let me just pause this and we'll tell you exactly why it's super important.
Knees weak, arms are heavy. There's vomit on his sweater already. Mom's spaghetti, he's nervous, but on the surface he looks calm and ready to drop bombs. But he keeps on forgetting what he wrote down. The whole crowd goes so loud, he opens his mouth, but the words won't come out. He's choking how? Everybody's choking now.
Alright, I'm ready to drop bombs here. The importance of the mean value theorem is that it delivers the Ninth Symphony for the 17th century. That, my friends, the Ninth Symphony for the 17th century, the greatest creation of humans during that century, is perhaps the fundamental theorem of calculus. It changed the way we do everything in life, the way we do science, the way we, all sorts of technology was advanced. Everything changed with the fundamental theorem of calculus. That's the time, I told you calculus has two super huge questions. the question of tangent slopes and the question of errors under the curve. That's what I told you the first day, right? Remember? And we've done the tangent slopes. We've pretty much beaten that horse to death. We've done so many things on tangent slopes. We're about ready to start on the area problem. And the area problem has this very, very elegant conclusion, which is known as the fundamental theorem of calculus. That, my friends, that's got to be one of the most significant breakthroughs. Not just a breakthrough for the sake of technology, but just on its own, a really, really nice and elegant idea. That's why it's called that's why I call it the Ninth Symphony of the 17th century. And the way we prove it is no more, no less than the mean value theorem. That's why they call it the midwife. By itself, it's not that. This one right here, they always call it the midwife. I think I've called it that before. By itself, it's not that big of a deal, but it delivers big things. It delivers big things. That's the importance of the mean value theorem. Now, maybe I would like to take. No, not maybe. I would like to take about 3 or 4 minutes to just plant the right seeds in your brain. To see exactly where we're going with the mean value theorem. At first, it might look just like this, and for somebody who's not trained in this subject, they might think, whatever. The tangent slope is equal to a secant slope. It's not even a big deal. It's because this thing right here, it's not one of those things that are beautiful because they look beautiful. It's not like a peacock that goes off showing off its beauty. You kind of have to dig a little deeper and see. And so to show it off, and so that's what I want to do. Maybe dig a little deeper and see exactly what the power is of the mean value theorem. So the next 3 or 4 minutes is I'm not doing anything new. I'm just regurgitating the mean value theorem and just turning it around a little bit and looking at it from a different point of view, which will be the most useful point of view, of course, for the Ninth Symphony of the 17th century. Okay. By the way, this is Eminem's Ninth Symphony. Alright, so let's do it. Let's unleash the power of the mean value theorem. As it stands, it's not that big of a deal, but what happens when you move, or suppose I multiply both sides by the quantity b minus a and b minus a. If I multiply both sides by b minus a, I get this new version of the mean value theorem, which is not that different than before, but it's just a slightly new version. This version turns out to be a lot more powerful. And it becomes more powerful when you start looking at it as sort of an exchange rate. It's telling you that every single time you have, by the way, you can do this with any equation. If I tell you A is equal to K, I'm really giving you an exchange rate. I'm telling you every single time you see an A, it's the same as K. So you could replace it, take it away, and replace it with a K. It's an exchange rate. Every time you see a K, you can, if you want, take it away and replace it with an A. They're equal values. So this is an equal exchange rate. If you look at it that way, it becomes incredibly powerful, because this tells you that every single time you've got something like f of b minus f of a anywhere, and we will have it somewhere, believe me, we will be able to, if we want, exchange that, throw it away and exchange it for f prime of c times b minus a for an adequate c. Okay? If you start to look at it that way, you start to unleash the power of the mean value theorem. And you have to be good with this idea, so good that you can apply it to other things, not just a function f of x. So this version of the mean value theorem becomes much more powerful. The idea that you can exchange, we can exchange this guy right here, f prime of c, which is some tangent slope times the length of the interval here, b minus a. We can exchange that for f of b minus f of a. And again, the thing to observe here is that this guy right here, this function, is the derivative of this one. The one on the left is the derivative of the one on the right. But again, we got to take that to the next level. What if it was a g? Well, that would be easy. That would be g of b minus g of a. And what if it was an h prime? Well, that would be the derivative of an h without the prime. And I changed it up a little bit. Ooh, I almost got myself. Alright, you can keep switching it up. What if it was a capital RC? Well, that would be a capital R without the prime. M minus for the appropriate C, of course. All these are for the appropriate C. You get that. Again, these are just reincarnations of the same statement. But this is just a little appetizer what happens if I switch it up? What is this the derivative of? G double prime. Well, that would be the derivative of G single prime of B minus G of A. Again, the important thing to observe is that this one is the derivative of the one, whatever you got on the right hand side. If this one was a 100th derivative of C, this would be the 99th. Right? If this one was the third one, then this would be the second one. F double prime of B minus F double prime of A. Again, these are just reincarnations of the same statement. If this was a fourth derivative, then this would be the third derivative of B minus the third derivative of A. Again, reincarnations of the same mean value theorem. Trying to unleash the power, but the most interesting one is right here. This is the biggest unleash. What if I don't have a prime here? Whoa, 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 whoa. You see how all these other ones had primes here? They've had primes, and whatever primes you had here, you had one less prime over here. So in every case, this one was the antiderivative of that one. Whoa, I just dropped a bomb on you guys right now. I said the word antiderivative. I never said this word before in this class, but I'm saying it now. Whatever's on the right hand side is the antiderivative of this one right here. Do you hear what I said? It's the antiderivative. In every one of these cases, this one was the antiderivative of that one, or this one was a derivative of that one. Same thing. But they all had primes, so it was easy to see what the antiderivative was. What if it doesn't? Whoa, this is brand new territory for us. It is customary to name a new function. Sometimes you can and sometimes you can't. When you can, you call it let's call f of x a function such that if it exists, f or capital F prime of x is equal to f of x. That's the thing that f of x is the derivative of. If such a thing exists, let's call it f of x. In this case, then, this would be whatever this was a derivative of. We're calling f of b minus f of a. That's what the new souped-up version of the mean value theorem would say. It's not really new. It's just the same thing, looked at it from a different point of view. And that right there, that begins to unleash the power to deliver the goods, to deliver the fundamental theorem of calculus. But even then, that's not even the punchline. Let me get to the punchline already. To unleash the power, consider the super famous function. Let me pause here. Super famous function, the position function. By the way, this is huge, right? Let me put some music. That's huge. So I put some music on it. Consider the position function. Let's take the same scenario where you've got some poor soul here that's running away from home, from all the troubles. They're running and they're running and they keep running. And let's look at the time here. The time here in hours. Suppose that after 1 hour their position is, say, I'm just going to go with, I don't know. After 1 mile, they're so tired and worn out. They haven't walked that much. Maybe only 2 miles. They're at 2 mile mark. And say maybe after 5 hours, maybe they've gotten, let me see, that's 4 hours. They would probably, let's make them walk at, I don't know, let's make them run like at 6 miles per hour. 6 times 4 is 24, so that'd be about 26 miles away from home. This is the position. Okay? So then what does the mean value theorem say here? This is big, right? Pay attention. This is the punchline. Right here. Getting kind of nervous. Drop bombs. My arms are heavy. Mom spaghetti. But the words don't come out. Let me think. So what does the mean value theorem say? Hey, it says on the one hand, it says I can calculate the distance 2 different ways. Oh, this is beautiful. What? Not now. I can calculate the distance 2 different ways. Check it out. One way to calculate the distance, forget about this one, right? One way to calculate the distance is so easy, so plain, so elegant, so beautiful. It's easy. It's beautiful. I calculate the position after 5 hours. Hey, I was at 26 miles away from home. And then I think, well, where were you after 1 hour? Well, I was 2 miles away from home. 2 miles away from home. Let me think. After 1 hour, you were 2 miles away from home. And after 5 hours, you were 26 miles away from home. let me think. The total distance traveled was the difference. 26 minus 2. This is the distance traveled. Distance traveled is equal to 26 minus 2, which is equal to 24 miles, right? 24 miles. That's one way to calculate the distance traveled. That's half of the mean value theorem. But it is powerful, man. Look at this. Forget about that. Now let's look at the distance traveled a different way. This one says, you know what? That's silly stuff over there. I got a better way to calculate the distance. The distance traveled would be some point in the middle. I'll find the point where the instantaneous rate of change was equal to the total average rate of change, which was 6 miles per hour. I just multiply 6 miles per hour, and I'll multiply times the total number of hours. 5 minus 1, that was 4 hours. So that gives me a total of 24 miles. That's how much you traveled. See, you could get with this, or you could get with that. You could get with this, or you could get with that. On the one hand, you can say the distance traveled just, hey, it's so easy. Just tell me, what was the position? Where were you after 5 hours? Oh, I was 26 miles. Where were you after 1 hour? 2. Oh, okay, you traveled 24 miles. You see how simple that is? Where were you after 5 hours? Oh, I was at 26 miles. Where were you after 1 hour? Oh, I was at 2 miles away from home. Oh, you must have traveled 24 miles during the first and the 5th hour. That's easy. This is just as simple and it's just as beautiful. What was the average that we were going at? Oh, I was going at an average of 6 miles an hour. And how many hours did you travel? Oh, 4 hours. Oh, okay, you traveled 24 miles. So simple, so elegant, but that's nothing. Wait till you see what's coming up next. That's nothing. Okay, let me drop some more bombs. I'm ready. Because I can't grow old in Trailer's Lot. Salem's Lot. You guys ready for the punchline? This is not even it. My hands are shaking. My arms are heavy. Something amazing happens when you turn this into an area problem. Every single one of these slope problems can be turned into an area problem. What if you graph the velocity? This is p prime of t. This is a velocity function. Compare it with a time function from 1 to 5. Suppose at 1 you picked up, you were kind of slow, then you started traveling really, really fast. This is the velocity, and then you got tired, and maybe you took a little rest here, and you're pretty much you were traveling at 0 miles per hour. Then you picked it up and you started accelerating, and then you went down, and then you whatever, and then after 5 hours you got tired and you just went down. What if that's the way it went? Wait a minute. We have no clue. When we set up the scenario, we have no clue whether you stopped in the middle or went or you rested or you started running or you hitchhiked. We had no clue what happened here. Nobody said anything about that, and it frankly didn't matter. It mattered where were you after 5 hours and where were you after 1 hour, and take the difference. Whoa. Take it easy. That means that, wait a minute. On the one hand, this is the average speed. On the other hand, this is just the position at the endpoints and the difference. But on the other hand, it has a connection with the area. This has a connection with the area. And the connection is that every one of these little pieces of area, is a rate times time. What is rate times time? Well, that's equal to distance, right? If I added all these chunks up here, the total area under the curve, what's another name for the area under the curve? Rate times time. If you have rate times time, that area happens to be the distance traveled. But wait a minute, what was that over there? What did we just calculate? That was the distance traveled. But wait a minute, what did we calculate over here? Oh, that was the distance traveled. They're all the distance traveled. Whoa. Easy. Every one of these quantities is the distance traveled. 24 miles. This is 24 miles. And this is 24 miles. Did we just calculate a super gnarly curve area? Did we just do that? I thought these kind of curves were for grown-ups. Remember the first lesson that told you that areas are so difficult? That was one of the fundamental theorems, one of the fundamental questions of calculus. The idea of calculating these areas that are incredibly difficult to calculate because they're not rectangles or triangles or shapes like that. This area could be as crazy as you want it, and just like that, but power of reasoning, I just calculated the area. The area is equal to the distance, and the distance was the difference of the position function. Boom, there it is. That's a little tiny baby little taste of the fundamental theorem of calculus. Isn't that amazing? The area could have looked like this. Okay, I don't care. The area could have looked like this. Okay, I don't care. Whatever the area looked like, I just calculated it by just knowing the antiderivative and evaluating at the endpoints. Oh my goodness.